purpose of today's lesson is to understand the impact on the change to the area and perimeter of a figure when it has undergone a transformation that is a dilation. And what you should recall is that when we have a dilation, we are creating similar figures. So what we want to do is, on the graph below, graph two squares, one that measures 3 by 3 and the other that measures 9 by 9. Where you put them does not really matter, as long as they are 3 by 3 and 9 by 9. So this is where I'm putting A, B, C, D. And then I'm going to put W, X, Y, Z. I'll move it to the outside a little bit so they don't intersect. So I have a 3 by 3 and a 9 by 9. Apologize for the messy lines, but the point gets across. Now, we want to answer following questions. What is the area of, are the squares similar to each other? I'm sorry. The answer is yes, and what you should see is that the blue square is 3 times the first one. So there's been a dilation with a scale factor of 3. And in fact, all squares are similar to each other because they have 4 equal sides. Now we want to compute the perimeter and area of each of them. Well, in the first one, it's a 3 by 3. So the area of that one is 9. The second is 9 by 9. So its area is 81. The perimeter, which is adding up the sides of the first, is 12. And of the second is 36. Now, we want to make sure we understand that relationship and the scale factor. We said the scale factor was 3. So hopefully you're seeing, let's take a look at the perimeter first, that 12 times 3 gives me the 36. However, that doesn't work for the area. And hopefully what you're understanding is that when I triple the size of each side, I'm doing that for 2 sides that get multiplied by each other, as opposed to adding the 4 sides. So, what is our conclusion? Well, the first one is that if in terms of the perimeter, if 2 figures are similar by a scale factor, then the perimeter of one is equal to the perimeter of the other times the scale factor. So, our little formula, perimeter of the original times scale factor equals the perimeter of the image. Okay, now, hopefully you are realizing that that's not going to hold true for area, but there still is a formula. So, let's see. If 2 figures are similar by a scale factor, then the area of one is equal to the area of the other times the square of the scale factor. So that formula would be the area of the original times the scale factor. I need to spell that correctly. Squared is the area of the image. So if you looked back at the problem we did at the very beginning, if you took the scale factor of 3, squared it, because we changed the length and the width, that's 9. 9 times the 9 is the 81. All right. So I have two similar rectangles. The scale factor of the two is 4. The perimeter of the smaller is 14, and the area is 12. And I want to find the perimeter area of the larger. So let's lay out a little chart here. Smaller, larger, perimeter area. So the perimeter is 14, the area is 12. Okay? So how do I find the area of the perimeter and area of the larger? Well, for the perimeter, it's simple. Multiply it by the scale factor. For the area, it is also simple, but you have to remember it's times it by 4 squared, which is 16, which gives me 192 units squared. Okay? Example 2. Two rectangles are similar. One has a length of 6 and a perimeter of 24. The other has a length of 7. What is the perimeter of that rectangle? Well, what I want to do now, length of 6 compared to a length of 7, perimeter of 24, an unknown perimeter. I can set up a proportion because everything is proportional. So 6 is to 7 as 24 is to the unknown. Cross multiply. 6x equals 168. So the perimeter of the other is 28 inches. Okay? Let's go to the next example. I have two triangles, and I want to know the perimeter of triangle DEF. Well, the first thing I want to know is what's the perimeter of triangle ABC? I add up the 3 sides and get 24. Now, the simplest way is I can set up a proportion. 6 is to 9 as 24 is to x. Cross multiply. 6x equals 216. And I get x is 36 inches. Now, another strategy that could work in this example is I could have found the other 2 sides, this side here and this side here, by setting up proportions and then adding that result. But you'll see what I did was clearly the quicker way to do it. And you'll see from the next example where what I did above can only be done here. All right, let's say AB measures 18 units and DE measures 24. And the perimeter of DEF is 64, and I don't know this one. You'll notice I put the information all around the triangles. It makes it visually easier to see how to set up a proportion. So my proportion, 18 is to 24, as x is to 64. Cross multiply and divide. And I figure out that 48 units is the perimeter. Okay. Finally, to summarize, what happens is when I change my length, width, and perimeter by a scale factor of k, the length, width, and perimeter all change by that amount. But the area changes by k squared. So if I have a scale factor of 2, my length, width, and perimeter all double, but the area goes up by a multiple of 4, or 2 squared. The same thing, if it's 4, length, width, and perimeter all go up by a scale factor of 4, but for the area, it's 16, which is 4 squared. And then finally, if I have a scale factor of a half, that changes the length, width, and perimeter by a half, but the area by 1/4. How did I get 1/4? 1/2 times 1/2. Okay? So to summarize, when dealing with similar figures, to figure out the change in perimeter, it's the image of the original figure's perimeter times the scale factor gives you the new one. But if it's the area, it's the original area times the scale factor squared that gives me the new area.